So I'm now about to start the 5th chapter on our course on solid state physics. And of course, you can see that the chapter we will be discussing next is called the electronic properties of solids. So in essence, what we will be covering in the upcoming lectures that we will go speaking first of all about the key assumptions we will be doing in the approach. And then we will say a little bit about the idea of energy bands. And after that, we go to the actual main topics of this chapter, which are the free electron model. And then in FYS.310 and the subsequent subsections, the nearly free electron model. But what I will be speaking here in this very first lecture, I will be going through the key assumptions that we will be using in our approach and in the treatment. So mainly these will be the approximations, assumptions we do in our treatment in this chapter. And this chapter, of course, focuses to provide understanding of the electronic properties of solids. And mainly we're speaking of metals here. So that's the starting point that we have. And essentially what we will be doing here in this section is that we will be extending the classical Drude model a bit. And that's the main outline in a nutshell that we will be doing in this chapter. And in what follows is that we will assume a so-called Born-Oppenheimer approximation. And then we will consider basically only single electron wave functions. And we discover that this approximation already provides us the energy band structure of solids. So essentially how the electrons form bands and how those bands affect their macroscopic properties. We will neglect the electron-electron interactions in the upcoming sections, and we essentially assume that our solid will be a perfect crystal. So meaning that we have an ideal periodic lattice that we will be dealing with. And we won't be dealing much with impurities and defects, although in the very final section regarding the transport properties, we will be speaking a little bit about their importance also when we would be measuring and trying to understand the real electrical conductivities of metals and solids. And now with these assumptions at hand, then we're ready to really go and solve the Schrödinger equation and then use the Pauli exclusion principle and of course take use of the Fermi-Dirac statistics so that we can operate at a finite temperature of a solid and not at 0 kelvins. And then we can calculate the final single electron state populations that we have in the electron energy bands that we will be covering. So this is in a nutshell what we will be learning in this lecture. So like I already said, this chapter, what we have here, this is really devoted to form a treatment to understand the electronic properties of solids. That's the main thing that we want to cover here in this section and this chapter. Here we will really focus on metals and subsequently we're really interested in the electronic properties of metals that can be already quite well understood using the classical Drude model in case you are already familiar with that, probably by encountering it earlier in other courses that we have in our university or elsewhere. And what we will do here in these upcoming lectures is that we will we'll develop a quantum mechanically correct version of the Drude model, a so-called Drude-Sommerfeld model, or nearly free or just free electron model. And what this allows us, well, first of all, it, for example, solves the disagreement that we had in the Dulong-Petit heat capacities when we would be trying to understand the heat capacities of metals by just using the classical Dulong-Petit approach. And then we kind of understand that how come there's this prediction from the Drude model where we assume that we have free electrons present in a metal and then the expected heat capacities based on the Dulong-Petit, we realize that there's actually no disagreement when we just extend our model a little bit from the classical Drude model into the more quantum mechanically compatible version of it. And what we will do is that, of course, in principle, what we should do is that we should really solve a many-body Schrödinger equation. And here, many-body means really many electrons involved. And in principle, like if you would like open that door, we would realize that even in a small piece of a solid, we would actually have an insane amount of electrons there, and easily we would end up in a situation that where does this extension stop? And what we don't do here is that we don't solve many-body Schrödinger equation. We will just really focus on a single electron state and work on that. But if we would do that, if we would really solve a many-body Schrödinger equation, we would find electron wave functions psi's, and we would find their associated energy eigenstates E, and then we would see how the system would behave, because essentially in quantum mechanics, usually you're done in solving the issue when you have solved the Schrödinger equation that you are dealing with. Of course, the problem here is that we should really consider, at least in principle, all the electrons that we have in the system and all the ions. So essentially the lattice, the ionic lattice that forms the periodic structure. And then even though we're dealing with metals and essentially the conduction electrons, we should also take into consideration the fact that we do have electrically charged periodic lattice of ions. And that gives us problems in our treatment. So what we cannot really do if we would try this fully rigorous approach is that we would really end up into issues, actually into huge issues, if you would want to solve something analytically. And even though in real life and in research, we quickly go beyond analytical models, analytically solvable models, and we can do, of course, numerical simulations, numerical calculations, estimates, and that could give us better predictions of systems. But in a course, that approach usually or many times doesn't really provide us good intuition and understanding of things. And that's why in practice, in many courses, when we are dealing with things, we prefer analytical models because they can provide us usually very good intuition and understanding of what happens in our system of interest. And that's one of the kind of motivations why so many times in a course we are dealing with very simplistic systems, because usually those have been chosen and realized that they are systems that are good enough to tell us roughly how the nature works. And in this approach, what we need to do is that we really need to simplify things, our system, by making these approximations so that we can still have an analytical or at least roughly analytical system, and that can provide us better understanding and predictions of our response. And here we are really interested in this chapter on the electronic properties of solids, of metals. So how, in essence, metals conduct electricity. That could be the kind of main one question we want to answer here on this lecture. Sorry, not on this lecture, but on this chapter, on this series of lectures. And what assumptions we do? First of all, let's note that the mass of an electron is very much smaller than the mass of a proton and a mass of a neutron. So when we compare the masses of conduction electrons with or against the masses of nuclei, that usually means many protons and many neutrons, then really the mass of an electron is insignificant compared to the mass of the nuclei. And then this implies to us that only it's the electrons that move when we would be forming an equation of motion. And then when in that equation of motion, we would be dealing with a electron motion with respect to the nucleus. So ionic cores, in essence, they are assumed to be stationary, which of course is not entirely true, but it's an assumption, and it's a fairly good assumption to make as long as the mass of an electron is vastly smaller than the mass of the nuclei. And this approximation is known as the Born-Oppenheimer approximation. So in case somebody is asking, you remember that this is exactly what we were speaking. So we assume that the nuclei are heavy compared to the electrons. Second, what we do is that we will neglect in upcoming lectures the electron-electron interactions. So in essence, what we do here is that we will be only considering single electron wave functions. So we do not consider like many body electron physics here. So like if you know something about solid state physics, then you would, for example, realize that this treatment won't be enough to explain, for example, what are MOT insulators and such things, or like how come, for example, some materials turn into superconductors when the temperatures are low enough, but these effects won't be considered here. And other electrons, and of course the ions that are still present there, we assume here, since we are dealing with just single electron wave functions, that the only way that these electrons and the ions can affect the movement of conduction electrons is via the potential function U that we are putting into the Schrödinger equation. And with this, what we can do is that we can then write a time-independent Schrödinger equation in a familiar form, where we have the kinetic term times the psi, and then we have the potential function multiplying the psi. And then on the right-hand side, we have the energy eigenstate. So now of the Schrödinger equation, we get the eigenvalue for the energy of this specific wave function. And most of the treatment here, we will be just assuming that our potential function is 0. And then we will be dealing with the free electron model. And then later on, we will assume that what if it is non-zero small periodic potential, what then will happen for our toy model that we will be describing. So that's what we will do in the upcoming lectures. And then the final point to kind of assume in our treatment is that we really want to restrict our treatment to periodic solids. And here, essentially, in essence, we mean crystalline materials. So crystalline metals, so to speak. And with this, what happens for the piece of mathematics is that everything, of course, all the functions that we are dealing with, because all the physics we're dealing with are periodic, lattice periodic, then the potentials, the wave functions, and all the other properties that we have that is describing the system, they are restricted by the periodic boundary conditions. So essentially all those functions are lattice periodic functions. So mathematically that means that, for example, like if you would have a non-zero periodic potential, then UR would be exactly the same thing when we would be going into a position of R, where R is a lattice vector associated with the lattice. So that's the periodic boundary conditions we impose. And of course, same way, the psi, the wave function associated with our single electron, that must be lattice periodic, so that the wave function in a position small r must be exactly equal to the psi, the wave function in a position of r plus capital R, where r is our lattice vector. And recall the definition of the lattice vector so that they know that this is actually quite a bit of a limitation for the form of our function. And because of this periodicity that we have for the problem at hand, we can simplify the math, or maybe not simplify is not the better word here, but we can really power up the math that we're dealing with by taking use of the Fourier series description. And that will be an extremely powerful mathematical tool here that we will be having in these upcoming lectures. And please distinguish here what is the difference between a Fourier series and a Fourier transform. So like what is the difference between these two different mathematical tools? And then remember the Fourier series is the one that we are using when we're dealing with periodic functions. And when we are dealing with not periodic functions, then we will be using the Fourier transforms. And now what we will do in what follows is that we will solve the time-independent Schrödinger equation. And before we get started, let's just recall that the Schrödinger equation that we are then dealing with, in essence, it's an eigenvalue problem, so that we have our wave function psi I related with a given energy EI. This wave function is our eigenvector if we would be thinking this problem as an eigenvalue problem. And then the associated energies that we will solve, so EIs, these are our eigenvalues of the system. So in case you're familiar with eigenvalue problems, then you know that you are now with a familiar topic mathematically. And of course, we can take use of the mathematical treatment associated with eigenvalue problems and use all that powerful math to understand how we solve the Schrödinger equation. And then when we are done, we have a solution for a single electron. Then we will need to populate our system with the n electrons that we have. And since the electrons are seen half fermions, we must take use of the Pauli exclusion principle in order to populate the found out energy states of the system with electrons. And here we are really strongly basing our approach to the single electron approximation. So we just solve the single electron states of our system, and then we just populate these states with the electrons. And we do not consider the fact that when we start putting in more electrons, these electron states could, for example, hybridize, and that might change things in our treatment. And of course, in reality, this kind of hybridization does occur in quantum mechanical states. So, for example, recall sp3 or sp2 hybridization of wave functions, electron orbitals, when we are dealing with appropriate carbon structures. So, for example, with diamond, the structure of diamond is being dictated by sp3 orbitals, and with graphene, a single layer of graphite, then we are dealing with sp2 hybridized electron orbitals. So those are, for example, examples of physics of many electrons, many body physics with electrons. But those we won't be really covering here. Rather, we're just using the assumption that we're dealing with single electron states. And then, this Pauli exclusion principle and whatnot, solving the Schrödinger equation, this is fine, especially when we are dealing with close to 0 temperature kelvins. But when we go to the finite temperatures, and we will do so, then we will also need to apply the Fermi-Dirac statistics in our treatment. So essentially, what happens nearby the highest electron states and their energies, there will be some kind of statistical fluctuation in the states. So some states will absorb a little bit of thermal energy from the environment and will be excited into a higher energy state. And then after some time has passed, this higher energy states will be relaxing to the lower energy states. So there will be a little bit of a kind of blurriness nearby the highest energy level that is known as the Fermi energy EF of our system. But more on that, of course, later. So these are what we will essentially assume in our approach. And next, after we talk about the idea of energy bands, we actually start with our mathematical treatment. So please, I hope you enjoy the ride what follows. Thanks and bye-bye.